We're going to continue our kinetics discussion by talking about what is a reaction mechanism. And this is a multi-video topic. Though we see the overall reaction when we see a chemical equation, the overall reaction might require more than one step. The listing of the steps is called a reaction mechanism. Each step is called an elementary reaction. Reaction mechanisms are proposed and then tested. Now, in order for a proposed reaction mechanism to be valid, there are two requirements. The first is when you add up the elementary reactions, you must end up with the overall reaction. And the second is the proposed differential rate law based upon the reaction mechanism must be identical to the experimentally observed rate law. If the proposed rate law does not meet either one of these requirements, it is an invalid reaction mechanism. There can be more than one valid proposed reaction mechanism, and to determine the correct one requires experimental investigation, which we won't go into. And it is possible for a reaction mechanism to consist of only one step. Let's take a generic equation. A sub 2 plus B sub 2 becomes 2AB. A mechanism is proposed. In the first step, A sub 2 decomposes to A plus A. In step 2, A reacts with B sub 2 to form A B sub 2. And in the third step, A B sub 2 reacts with an A to form 2AB. You notice here that the A's cancel out and the AB sub 2's cancel out. So when you add up the equations, you get A sub 2 plus B sub 2 becomes 2AB, and this is the known overall reaction. So this meets the first requirement. Those chemicals that were crossed out, the A's and the AB sub 2's, are called reaction intermediates or just intermediates. Intermediates show up on the product side of one step and are eliminated on the reaction side of a later step. We will talk about the molecularity of the steps. The molecularity is the number of reactant particles involved in an elementary step. So if we go back to our previous equation, we see that the first step only has A sub 2. There's one particle, so that is unimolecular. In step 2, we have two particles, A and B sub 2, so that is bimolecular. In step 3, we have AB sub 2, which is one particle, plus A, which is a second particle, that's also bimolecular. You can occasionally have a step where there are three particles, or termolecular, but these are very rare, and the chances of having four molecules collide with the correct energy, all hitting at the same time, is so rare that we can say it does not occur. Now, for an elementary reaction, unlike the overall reaction, the rate law for that step is based on the stoichiometry. You take the concentration of reactants in the elementary step and raise it to the power of the coefficient. So going back to our generic equation, for step 1 here, we would say the rate law for step 1 is rate equals the constant times the concentration of A sub 2. In step 2, the rate would be equal to a rate constant times the concentration of A times the concentration of B sub 2. For step 3, the rate law would be rate equals a rate constant times the concentration of AB sub 2 times the concentration of A. As a general rule, if you have a unimolecular elementary step, the rate law is K times the concentration of A. For bimolecular, you could have two of the same thing. Because there are two, it's bimolecular, and the rate would be K times the concentration of A to the second power. You could have A plus B becomes the product. That's also bimolecular, and the rate is equal to K times the concentration of A times the concentration of B. You could have three of the same thing colliding to form the product. That would be termolecular and would have this rate law. You could have 2 and 1, once again termolecular, with a rate law that has the concentration of A squared and the concentration of B to the first power. Or you could have three different reactants. Because there are three, it's termolecular, and the rate would be the rate constant times the concentration of each of the reactants. But do remember, the termoleculars are exceedingly rare. So here is an example of a problem you might get. For this reaction, this is the proposed mechanism. There are three questions for you. The first, when you add this up, do you get the correct overall reaction? Secondly, what is the molecularity for each step? And third, what is the rate law for each step? Stop, answer the questions, come back, and see how you did. Go. Let's start with the first question. Do you get the correct overall reaction? Well, here are the two steps, and you can see that the singlet chlorines are an intermediate, and so they cancel out. When that happens, you get this equation, which is the same as the overall equation that you expect. So we can say that you do get the correct overall reaction. Question number 2, what is the molecularity for each step? Step 1 is unimolecular. It only has the NO2Cl. Step 2 is bimolecular. It has NO2Cl and singlet Cl. What is the rate law for each step? For step 1, which is unimolecular, the rate equals K times the concentration of the NO2Cl. And step 2, which is bimolecular, has the rate equals K times the concentration of NO2Cl times the concentration of Cl. So based upon what we know at this point, this is a valid mechanism. So to review, a reaction may require more than one step, but it might only have one step. A reaction step is called an elementary reaction. Reaction mechanisms are proposed and tested, and there are two requirements which must be met for a proposed mechanism to be valid. The sum of the elementary reactions must add up to the overall reaction, and the proposed differential rate law must be identical to the experimentally observed rate law. And in this video, we only looked at the first requirement. Subsequent video will look at the second requirement. There can be more than one possible reaction mechanism. If there are multiple steps, the chemicals which cancel out when you add the equations are reaction intermediates. The molecularity for each step equals the number of particles of reactants. If you have one type of particle, it's unimolecular. 2 types is bimolecular. 3 types is termolecular, and these are rare. The rate law for an elementary reaction is determined from the elementary reaction stoichiometry. You just take the concentration and raise it to the power of the coefficient, and that covers the first requirement. In the subsequent video, we will look at rate laws.